Hey, hi there. Welcome to the probability distribution video, second part. Today we'll be talking about continuous distributions. So under continuous distributions, we looked into standard normal distributions, right, in the theory lecture. So let's work on it. I'll import all the necessary libraries. I'll import again the same function, import scipy.stats as st. From this particular function or library, whatever you call it, we'll import all the other necessary probability distribution function with respect to which we can calculate the probabilities, of a standard normal distribution. Suppose that, so now I'll take the first example which I'll take will be with respect to the one which we had already covered in the slide of the theoretical class. Now, what was the question? Suppose the current measurements in the strip of wire are assumed to follow a normal distribution with a mean of 10 milliamperes and a variance of 4 milliampere square. What is the probability that a measurement will exceed 30 milliamperes? Now, as we all know, in probability distributions, especially continuous distributions, we do not calculate probability of an event at a particular point, right? We always calculate between a range or less than or greater than whatever it is. Typically, we calculate cumulative probabilities in continuous distributions. So here my mu is 10, my sigma will be root over 4. Root over 4 can be written as 4 to the power of 0.5, right? So sigma will basically be 2. And my x is 13 because that is the point after which we want to calculate the probabilities. So in this case, if I draw, it'll look something like this, right? So my mu is, say, 10, sigma is 2, and here is 13. So what's the probability that it will exceed 13? This is what we want. And we all know that we need to convert this to a standard normal distribution so that we can refer to a table. But here in Python, we do not require any table to be referred to calculate the probabilities. Here we already have predefined functions, inbuilt functions, which you can use, but those inbuilt functions are for the standard normal distribution, which means that we need to convert this original distribution to a standard normal distributions. So my 13 will become z equal to x minus mu by sigma. So x is by 10 minus 13 divided by sigma, which is nothing but 2. X is 13, sorry, x is 13, x minus mu is 10, right? Okay, so this will be 1.5. So my z is actually 1.5. So my new distribution, which is a normal distribution, standard normal distribution, mean is always 0, sigma is 1, and this is 1.5. This is the value of z. Earlier it was 13 for x, now this z is 1.5. This is the probability which we want. With respect to this, typically we try to find out the probability from the z table. So if we go back to the question, this was the question which we had, right? And we can see here the x is converted to the z range or the z scale. So now, in order to find out this distribution or a probability of z greater than 1.5, this is what we want. Just like in the table where we have all the probabilities for z less than a particular value of z, right? Always less than values are given. Similarly, in Python inbuilt functions also, less than values are given, right? So I have to convert this to a format where I can calculate probabilities of z less than a particular value, right? So this is what I have to do in the first case. Same thing which we had done before. Now the probability of this can be easily found out using a function, okay, which is called as norm.cdf, because it's cumulative. Norm.cdf. Earlier it was binom.pmf, right, or binom.cdf, whatever it is, Poisson.cdf. This is norm.cdf. So this is norm.cdf of z. Z is nothing but here 1.5. Once we do this, we'll get the answer to be, okay, let me just quickly import the necessary libraries, fill up the values of mu and sigma. So now my answer will be 0.6, or this is 6%, 6.6%. So if you look at the answer, it's 6.6%. Okay, so this is what we get. So it's very simple, guys. Same thing. Earlier we were using a table. Now we do not need to use a table. We can simply calculate based on the function. So earlier, if you look at 1.5, right, z less than 1.5. So this is 0.9332, right? So this value should be 0.9332. You can see it's 0.9332. Same which we had got from the table. Correct? 1.5. Right? This was I was showing for a different question, I believe, but this is what the answer is. Okay. Now let's take up some more examples. Let's sort this problem out. P of Z greater than 1.26. Let's check. Okay, let's check some more questions. Which was the slide? The slide number is, I believe, 12. Okay, slide or page 12. So the first one is P of Z greater than 1.26. P of Z greater than 1.26. Next is P of Z less than minus 0.6. P of Z less than minus 0.86. And P of Z greater than minus 1.37. P of Z greater than minus 1.337. And this will be 0.86. Anything else here? No. One more thing which I want to mention here, guys, is that, okay, that's correct. So P of Z greater than 1.26. How will I calculate this? Very simple. ST dot greater than. So of course we have to convert it to 1 minus. Okay. ST dot norm dot CDF of what? Of 1.26. Right? Okay. Because my function gives me values less than. But I'm asked about this point. So I'll do 1 minus, subtract all this region. I'll get this particular part. Right? Which I've already explained in the theoretical class very significantly, right? So this is what my value will be, 10% probability, 10%, right? Next, I have P of Z less than minus 0.86, less than minus 0.86, great. Less than values are already calculated from the table. Let's see if we can directly calculate this, right? Minus 0.86, 19%. 19%. So unlike in the positive table, because we had a table which is positive, we had to convert it to the either side and the positive side and again subtract. It's a lengthy process. But here it can take in negative values as well. Of course, we have Z negative table, but you have to keep on referring to a negative table separately to calculate Z less than a negative value. But here, one single function which can tackle with both positive and negative values of Z. Okay. This again, greater than means directly subtract it from 1. st.norm.cdf. st means the stats module, right? So here you can directly put minus 1.37, right? 91%. 91%. Exactly correct, right? So this is how you calculate a probability with respect to a cumulative interval of Z values, right? Okay. So now let's take another example. At the conclusion of a course is business statistics. A group of management students, sat for a written examination. The results throw up the following information. Marks obtained have a mean of 60 and a standard deviation of 12. There were 300 students who wrote the exam. The pattern of the marks follows a normal distribution. It is already given. What is the percentage of students who scored more than 80? What is the percentage of students who scored less than 50? And what should be the distinction mark if the highest 10% of the students are to be awarded distinction? Graphical method can be used for convenience. Okay, no problem. Now, if you look at this particular, question, the first two questions are again what they're asking is nothing but probabilities. Percentage is nothing but probabilities. P of Z, P of X greater than 80, P of X less than 50, whatever it is. But the third question, if you look at it, what should be the distinction mark if the highest 10% students are to be awarded distinction? This is where you are asked the Z value or the X value, right? The marks given the probability. यहाँ पे उल्टा question पूछा गया है. In the previous questions, in all of them we are calculating probabilities, but here we need to calculate the X or the value of the X, right? Okay, so let's now try to understand. So here we typically use, stats.norm.cdf to calculate P of Z less than Z. So in order to calculate this, we have to use 1 minus stat dot. That is something which we have already understood. So given here is mu equal to 60, sigma is equal to 12. So what is the percentage of students who score more than 80? So with respect to 80, which is X, I have to calculate the Z value. So my Z value will be 1.67. 80 minus 60 divided by 12. X minus mu by sigma. So score more than 80 will be 1 minus st.norm.cdf of Z. Very simple. So 4% people score above 80. Less than 50 will directly st.norm.cdf of 50 minus mu divided by sigma. So here my Z value with respect to X equal to 50 will be minus 0.83, right? And I can simply put it directly here because I'm asked to find out the probability of Z less than. So less than values, I can directly use the particular function because this function actually gives you probabilities less than a particular value of Z. This is 20% probability. Obviously, more number of people will not score that much good results, right? Only a few in every class are good. Now, the third question, what should be the distinction mark if the highest 10% of students are to be awarded distinction? Now here we have to calculate the Z value because my probability is given. So whenever you want to calculate the Z value, given the probability, you have to use st.stats.norm.ppf. Stats.norm.ppf. That is what you have to use. And inside, you can simply feed in the probability. Same thing which we did in the slides. We had to scroll across the table, right? And then we would find out, right, what are the values associated with it, right? Okay. So if I'm say given a probability of say the probability is given as 0.9861, what is the value of Z? You would scroll and then you can go to the value of Z. But here you can directly use a function which will give you the probability given the value of, which will give you the Z value given the probability. So probability is given as 0.10, 10%, 0.10, right? You can directly use st.norm.ppf. ppf will give you the probability. So once you get the probability, once you get the value of Z, right? Now here it may, now when you calculate the Z1 value here, please notice guys, that is giving me a negative value, right? But we very well know that once I get this value of Z, the next step would be to calculate the X, because the question is asking me the original data, right? In the original scale, not the Z scale. Correct? We're using the Z scale to get the probability, to get the value out using the probability, but ultimately we have to convert it to X. So X will be what? Z into sigma plus mu, because my Z is equal to X minus mu by sigma, right? So once we get this, if my Z value is negative, then what will happen? My X value will actually be less than mu. But for me to get a distinction, top 10%, right? Those students have to definitely score more than the average value, right? Which is the average value is around 60, right? Mu is equal to 60, sigma is equal to 12. So that will not hold good for us. So this Z has to be positive. This should be positive. So our sign is not a constant, because we know that highest top 10 would definitely have to score more than the average value. Or you can think of it in this way, right? Both sides, 10%, 90%, right? This area 10%, this area is again 90%. Top 10 people will obviously be scoring more than the average value. So instead of putting here 0.1, if I make it 1 minus, which is 90%, watch what happens. The Z will become positive. Same thing. Okay. Now I can run and check that my X has to be 75 marks, because this is on the Z scale. We want it in the original scale, 75 marks, right? So very few people who scored more than 80 right? If I run this again, because I had cleared out all the previous codes, you can see here 4% people actually scored more than 80, and all of these are distinction marks, right? And the top 10%, right, has to score 75 marks. Makes sense. Now, if I want to visualize this in the form of a graph, I can generate a normal distribution curve based on mu and sigma, right? How? I can simply generate it based on the uh, NumPy module, right? np.random.normal bracket में it requires three parameters: mu, sigma, and n. Okay, mu, sigma, because these are the parameters. Mu and sigma are the parameters of a normal distribution. So np.random.normal bracket mu comma sigma. Well, we also have to define the number of data points which we want. Okay, once we run this, and if I, simply plot the histogram of these values, bin is equal to 100, I've specified it. Okay, once I do this, I get the distribution curve. So what I can do here is I'll simply do this so that those values are not important for us to see, but this is how it would work. Okay, so if I want to recalculate the average of this distribution, I get it nearly 60. Standard deviation is nearly 12. To satisfy my previous condition of mu and sigma. Okay, so the function is np.normal. So np.random.normal of mu, comma, sigma, comma, how many data points you want. Very simple, right? And then I can simply do plt.hist on this entire array of data points generated using the NumPy module. Okay, right? Okay, guys. So now, right, clear. So I'll just put it like this. Okay. Now, if you really wonder in NumPy module, when we study the NumPy module, we in fact use NumPy module to generate random integers, random.randint, right? Then we generated, kind of decimal values, decimal points as well using the NumPy models. Just like we can generate random integers, we can also generate random normal distributed values from the NumPy module. So this is very handy, guys, right? So this is nothing but simulation, actually, right? Okay. Based on the parameters of the distribution, I'm simulating the entire data points, whose mean and sigma would be 60 and 12. So I hope you have understood today's lecture, because this is an earnest attempt to again fill the gap between what we learn theoretically and how it is actually understood in the real world. How do we apply it? And these functions, mind you guys, will be very handy when we do hypothesis testing, because there we have to calculate the critical value, the p-value, right? All those will be calculated, using some of these functions. Okay, so now if I ask you a question where it will mention, as in the previous example, what is the probability that a current measurement is between 9 and 11 amperes? Okay. Now, if I ask a question in the previous example, what is the probability that the current measurement is between 9 and 11 amperes? Determine the value of current for which the probability is 0.9. So there are two questions to this. First, it's asking the probability that a current measurement is between 9 and 11 amperes. And then it is also asking the value of the current for which the probability is 0.98. Okay. Now, this question is actually from the previous part, right? Where we had solved the question from the slide, which was this one. Okay. So let us put the question here itself. Okay. Let us try to solve this. So here we saw that the mean was 10 ampere, variance was 4, which means sigma was 2, right? So we already know mu and sigma here directly. Great. X was 13. So here my X1 and X2, there'll be two points here, right? There'll be X1, which is 9 milliamperes, and there'll be x2 as well, which is 11 milliamperes, right? Correspondingly, there'll be z1 and z2 as well. So z1 will be is equal to x1 minus mu divided by sigma, right? Similarly, I have z2 as well, corresponding to x2. That's it, right? Once I get this, so what is the value of z1 comma z2? Minus 0.5 and 0.5. Great. So I think I can easily explain this, minus 0.5 and 0.5. So if I have this curve, minus 0.5 and 0.5, this is 0, right? 0.5 will lie somewhere probably here, and this will be here. Correct? Okay. This region they're asking. Right? Okay. So if I find out this region and multiply it by 2, then I'll get this probability, right? Because either side, it is symmetrical. It has to be symmetrical. Standard normal distribution, theoretically symmetrical in nature. So if I find the probability between 0 to 0.5 and multiply 2, or 0 to minus 0.5, whatever it is, multiply by 2, I'll get the entire probability between minus 0.5 and 0.5, right? Now, if I want to find out this particular probability, how will I do it? Very simple. I'll simply write here, say, which means that for this, I need this particular area of probability minus this area of probability. This is definitely, the probability is 0.5 because it's half, right? Subtracted from the pz less than equal to 0.5. So what do I ultimately need to do? I ultimately have to calculate p of z less than 0.5 minus p z less than 0, which means nothing but this is 0.5. Right? The entire area on less than 0 will be 0.5, greater than 0 will be 0.5, equal halves, right? Total mila ke hoga 1. This is what I need to find out actually. And I have to, of course, multiply this entire difference into, because this will give me only the yellow portion. I have to multiply it by 2 to get the entire portion between minus 0.5 and 0.5. So how will I do it? Stats st dot norm, okay, dot cdf of 0.5. Let's say 0.5, positive 0.5, slightly greater than 50% because this is slightly greater than 0, minus 0.5. This is my area. Multiplied by 2. This should be my probability. And if you go here, this is in the slide, it is 38%. Correct? 38%. Very simple, guys. It's very, very simple, right? This is the first one. Second question kya hai fir? Determine the value of the current for which the probability is 0.98. Probability given is 0.98. Very simple. What will you do? Simply do st dot norm dot ppf to calculate z. I have to given the probability, I have to use ppf of 0.98. But this is z value, guys. Please understand this is z value, right? I have to convert this z to x. So what will it be? X will be x equal to z into sigma plus mu, and hence my x value will be 14.10. So if you go back to the slide, it's 14.1, 14.10, same thing, right? So this is how you calculate the probability respect to a particular value of z less than or greater than whatever it is, interval, and also how to calculate the z value given a particular probability. Okay, guys. So that's all for today. I hope you are learning and enjoying the sessions. This will probably, again, bridge the gap between what we learned theoretically and how we apply and in the real world, how we can use programming to easily calculate the probabilities and the distributions. So we can see here in this case, we don't need to refer to any table, right? These are all inbuilt functions available in Python. We can simply directly use them to get the required output. Even if you do not remember the exact function name, you can still search it in Google and extract it out. But you have to theoretically and conceptually understand what is the function doing. Unless and until you try to visualize this in the form of a graph, right? Or try to try to visually represent it, right? It will be difficult. So you have to do it so that you can understand things quickly and you'll never forget these concepts. These concepts will again be used in hypothesis testing, guys. Okay, so these functions are important. PPF, CDF, whatever it is. I have imported the stats as ST so that it becomes easier to write. But please don't forget this is a stats module from scipy. Okay. All right, guys. Then that's it for today. Okay. And keep practicing, guys. And stay tuned. See you in the next video.